I give it every 2 years. I've given it many times, over 100 times outside of here, and about 20 times in Europe. So it's been constantly updated for the last 25 years. And so I usually do it on St. Patrick's Day, but we couldn't get the lecture hall then. So we're going to go the day before St. Patrick's. And just understand that we're not selling anything here. We're just taking you to the grocery store. You can buy potato chips. You can buy beer. We're going to talk about God. We're going to talk about science. We're going to talk about all sorts of concepts. And you buy what you want, and I'll try to keep mine concealed to the end. And as I always say at the end of the lecture, I don't ask questions because I'm already going to tell you twice as much as I know, and at least 51% of it is right, I hope. Okay, so let's get underway with this. Okay, here we go. We're going to take you through a lot of mysteries. We're going to look into the dark parts of things, and we're going to try to see where are we today on many of these issues. And we want you to think beyond what you normally think. And every generation looks to the next generation. This generation thinks this new music is terrible, this new art is terrible, this new literature is terrible. But this discards what they don't want from here, even though this group's yelling, and moves to the next level. And every parent knows that who's ever dealt with it, and we did as young people. Now I have to move over here. I'm not sure I can see that from here. This says education. I have never let my schooling interfere with my education. Mark Twain. Education process and driving a sense of prejudice down your throat. Mark Fisher, education is an ethical thing, but nothing is worth knowing. Can be taught. Man, that's thank you. Can be taught. So from that, it would sound like what are we doing in the university? It's terribly important. We'll come back to that. Over here, convictions are more dangerous foes of truth than lies. And to be absolutely certain about something, one must know everything or nothing about it. So that's where we're sort of stuck as we head through this. And so we got to tell the liars and those who tell truth. And of course, statistics is a probability function, and much of what we're talking about cannot be put in quantitative terms, nor can it be analyzed by statistics. As you know, I have failed the 5th grade, 11th grade, C average from East Tennessee State. I hold 4 professorships now, never had a course in any of them. And the reason for that, of course, one, I'm dyslexic and read very little. And number 2 is I can do this. And very few people can do that. If you can do that, you can be a professor of ophthalmology in 4 years. Everything has a reason. Limited by I also was an engineer without an engineering degree. I headed up the engineering team and worked in space and didn't know anything about that either. So we don't have to assume anything because that you can prove doesn't make an ace out of you and out of me. So those are the rules we're going to try to abide by. And right away, we're going to find this is the biggest problem we face. And that is that we can't, our mind won't let us see what it is. We get these paradoxes that says, oh, I believe it's 3 cylinders, and then you spare 2 squares, and you just cannot figure it out. And seeing is not believing. Now, this is a little hard to see, but I'm going to ask you to do it. A lot of people have done this. Do not, is this off? Is this, I'm sorry, it should be on, so what's happening here? I have this on, so I have to look over here, is this correct? It's a little hard. A lot of people have seen this, but please bear with it. It has nothing to do with your intelligence. I want to ask you, without tricking you, to count the total number of F's in here. This is a very important principle, and it has a tremendous impact on science, on religion, and on everything. So we just take a minute to count the total number of F's inside this. I'll give you a second. Everybody has to vote. Okay, now what I want you to do is everyone who gets 3 F's in there, 85% of our medical students get when I give this to them every year. Hold up your hand. Hold up your hand if you see 3 F's in there. Everybody has to vote. Okay? How many see 4 F's? Okay, about 20. How many see 5 F's? About 25. How many see 6 F's? About 60, okay? Now, stop. If we can't reproduce each other's data any better than that, what does this mean, okay? And what it means is you do not see with your eyes, you see with your mind, and you only see what your mind lets you see, and you only hear at a cocktail party who's talking to you. And there's 6 F's in here, 1, 2, 3, 4, 5, 6. Now, the reason for this is that the human mind has developed the focus and to not see trivia. So your mind discards, and that's one of the big functions of the human mind, is it discards non-important information as it seeks the important thing. It's very critical for hunting, it's very critical for defense, and it's absolutely deadly for science. So you have evolved to do something different than your mind is, and that's why no one agrees on practically any piece of data or can reproduce each other's data. So seeing is all what you want to see, and you can read that as well as me. So now, human destiny. Who are we? Where are we? Where are we going? I've collected the thoughts and photographs of everybody I can get my hands on, and these are not my ideas. I'm just trying to put them all together for you. As I say, if you steal one thing, it's plagiarism. If you steal 100 things, it's research. This is a heavily researched talk. Over there, you can see on that slide, there's a lot of questions. Is there a theory of everything? Is everything one? Is there singularity? Is it quantum gravity? Who is God? What is God? All these questions. And so you have to have some faith in whatever you're doing. If you have faith in God, it's called religion. If you have absolute faith there is no God, it's atheism. If you think it can be done with the human mind by logic, it's called science, logical thinking. And indeed, you can do some of both of those. They're not exclusive. And in fact, Fred Hall, the great British astronomer, one of the top astronomers in the world, said, I've always thought that it's curious that while most scientists claim to eschew religion, it actually dominates their thoughts more than it does the clergy. And so here's Newton. I want to remind you, and this is Newton's manuscript of the Spectre, which he figured out, one of the great minds of all times. And as you know, he was quite a turkey. He took other people's data, stiffed them, tried to stop their papers, but he still was a wonderful scientist. On top of that, he discovered light, but light was here from the beginning. And so was DNA. So whatever we discover is what is already here. And so Einstein had many of these thoughts and wrestled with the same problems that you and I are wrestling with. And he said, I want to know God's thought, the rest are details. And so we come down to his hero. His hero was Ernest Mach. And this is the man who was named the speed of light after, so it's Mach 1, 2, 3, etc. So Mach said reality is what you can measure, and what you cannot measure does not count. Metaphysical says what you cannot measure, what really counts. And so we have to decide what we really think we should be doing here. And so these are the important things that cannot be measured. Love, music, family, friendship, happiness, beauty, sharing, laughter, comfort, health. Longevity can be measured in some of these, but some of these get to be a little hard to measure, to put qualitative terms on. And so what happened over the period of time as we went towards the unknown is we built the largest thing in every city on the world was a religious edifice. In fact, these cathedrals were the largest things that existed. And very quickly after that, they were replaced by the largest structures, which were usually large universities. And the universities were started by the churches, and there were church functions in the early days. That's why we have tenure. We think we're priests. You ought to come look at us. We're not priests. But anyway, the bottom line to it is today, the tallest building in every city in the United States is an insurance building. Okay? Now, I ask you, what is that reflecting about our culture? And it is that we think this can solve every problem. It can solve every problem of a university, every problem in a laboratory, every problem in a family, and this is a myth. And the reason it's a myth, it's only green paper. It has absolutely no value unless you believe it does. This is as big a myth as exists, and yet it's a very powerful myth. It's the way we trade and barter. And indeed, the flag of a country is a myth. It does not represent the country. Furthermore, the border that we put down the ground is a myth in a sense. It's something we made up. So science and religion can be compared on the sources, which in science are spontaneous and chance, and over here is planned and designed. The basis of this is physical, natural, and developing. Here it's spiritual, supernatural, and evolving. The truths are sought after in science and received in religion. The approach is skepticism, don't believe anything, test everything, and that gets us for our editors and our rank review people too. And faith and accept over here. The views of reductionist here go down to the smallest quark. The holistic view go up to the universe. The laws are pragmatic and changing and moral and constant. Response here is supposed to be human will and God's will. When you see those types of things, they very quickly cause you a difficult problem. Is how are we going to do these things together? And so now we're going to start with religion before we move on to science, and religion's changing. Now, it started out like this, and I think everybody agrees we haven't seen one of these in a few weeks, so that was the early religion. And then 2,000 years before Christ, 3,000 years before Christ was born, and 1,000 years before the pyramid, this came up on the scene. We still don't even know what that means, but that was quickly discarded. And then here are the great pyramids, when we believed that humans were gods and the pharaohs were gods. And here with Nikes and smoking a Marlboro with something written on top of the pyramid. Can you imagine that kind of disrespect for the pharaoh? And then, of course, here's some of the things that have happened in other cultures. And here are a couple of Buddhist monks sitting in this sort of what used to be an incredible temple for its period of time. And things are just changing. I mean, And a survey has changed in our religion. And that is the Judeo-Christian religion, which most of us here, although many Muslims in here and others, but in all these religions there's been massive changes. And these changes have come about and resulted in changes in religion of human sacrifice, animal sacrifice, sun gods, multiple gods, anthropomorphic gods, monarchs or gods, inquisitions, holy wars, buying redemptions, gender bias, hell is underground, and God is a local event. But over here in science, there have been tremendous changes in the concepts that have developed over here, all the way from alchemy down to the conservation of matter, and then with Freud showing that the mind is not logical, and so we've got some serious problems here on all of these. Now, if you're looking for the answers to this, don't come look in our laboratory. Dr. Walsh said, no, we didn't clean this up for our visitors. That looks like that. If you look in government, I had to pick a foreign government. And the reason I did that, I put up either Democrat, Republican, start trouble, but there are enough Japanese and Chinese in here to understand who these people are. But this is exactly what goes on in our Congress. This is a filibuster going on in Japan, and you can see that's the way they're making those decisions. But just because something's old and discarded does not mean that the values and the principles upon which this is based is not a very important event. In fact, the principles that came out of here, even though this is totally gone, are some of the most impact of mankind about freedom. And other things that came down through our religions have had tremendous impact on this earth. And so, why do we have to have morals and ethics and religions? Because born something between the ears of this little child has the ability to do absolutely incredibly good and bad things. Here are the good, here's the evil. We don't know what evil is, we don't know what good is, but here's some of them. Sing, nurture, love, share, create, knowledge, peace, clean, beauty, pleasure. Now these are good. Evil and negative things are insane. Now wait, is that evil or is that a gene? Murder, is that a gene? Hate, steal, destroy, ignorance, wars. All war, bad, no, dirty, ugly, and pain are things that we try to say are not good. And too much of that evil can cause big difficulties. And so this is some good. I think we all know it's like pornography, you know it when you see it. And this is evil. And it's hard to believe if we could focus that just a touch, if somebody could get to that, up there and focus that. This is, of course, Nazis killing 6 million Jews. Now, I want to remind you that this was done by a country that had more science, more religion, more family values, more discipline, more art galleries, and more music than almost any place on the world. And I am of German descent. It's hard for me to believe, Irish and German, that humans could do this to each other. But the American people in this room did this to the African Americans. About 6 million of those died in slavery. And it's hard to believe that Thomas Jefferson could write the things that he wrote about freedom on the Lincoln Memorial, on Jefferson Memorial, and have slaves. And my great-great-grandfather had a slave, and this is incomprehensible to me that any human being could do that. And so here is something that's not good. And this is a man's brains blown out. It's war. Now this is good because that's a Nazi, and we had to kill the Nazis to stop this, so this was good. But anybody who saw Saving Private Ryan knows that this is a very tough system. And let me tell you, war is hell. I've never been in it. Those who say that Private Ryan came close but didn't quite get the horror of it. Okay. So now over here, a lot of people pay the price for our freedom and the ability of us to enjoy this and proceed with not a barbaric approach. Now, by that time, of course, we're doing very well. As you can tell by my growth, I've eaten in this restaurant. But while I was eating in this restaurant, while I was eating there, just a few thousand miles away, this sort of thing was going on. The United States was storing wheat. Australia was shooting cattle because they couldn't get fair price on them. And this was occurring throughout the world. Now, about 1 billion people on this planet are undernourished. So the question is where are you in this? And just how much profit should you make? And there's no limit to the greed in the American marketplace. And of course, what drives the market is greed and fear is the hard part to put in. But as the Marie Antoinette and Louis XIV figured, and the people in Rio figured, you cannot have wealth next to poverty for long before the outnumbered ones in the poverty come to get their share of the wealth. And so we have to think about this. And these sort of things went on in the world. This is a Harvard graduate here smoking a cigarette. Just look out. We're doing things like this now, too. Can you imagine the type of racial slurs and insults involved in that type of photograph? And I don't have to tell you that having all the money and power in the world doesn't solve your family problems. Certainly not. And certainly the whole case here is not just to take care of ourselves, although that's what it seems like we're doing, And this is a couple of hippies that says, what future? And the question is, what future is there for all of this type of approach? And so, morals, what are they? How do you learn them? And where do you learn them? And are they constant? Do they come from science? They come from philosophy, from religion, or from experience, or a little of all of them? So now we're going to address the question, who has had the biggest impact? We're going to do a little science on this question. And these are people who have certainly had a big impact on this planet. And if I ask you to list the 4 people who had the biggest and longest impact and the most important impact on this planet, who would they be? And whoever they are, we should test what they did and see how that turns out. And the answer to that is you can put down a lot of them, but Carl Jasper, and there's references in these handouts to a lot of this stuff, compares this in sides that 2/3 of the people on this planet are Asian. They're not like most Caucasian, white, Southern Protestant Baptists like myself, but they're Asian, and Buddha and Confucius had a fierce impact on these people as lasted to this day. And certainly Christ has impacted on this base. Now, a lot of other people have had big impacts, but if he just had to pick 4, he picked Socrates because he initiated the type of thinking that led to the scientific method that gave us this laser beam that I'm flipping up here. And so we take a look at what they did, and what it turns out is how did they address money? How did they address education? How did they address power? How did they address public relations? And the answer is they didn't. In fact, what was their organization? They had none. They had no power. They had no army. They had no money, resources, property, or system. What did they say and write? They didn't write anything. The sword's supposed to be more powerful, the pen more powerful than the sword. They did not write. What did they interact with? Not with the nobility, the lost in the brains. They interacted with everyday people one-on-one. Christ interacted with the fishermen, Buddha with whoever met along the trail, Socrates with whoever met in the marketplace. They felt one-on-one interaction is the most important. And yet we try to get away from that and think that that's not so important. And what was the realm of their influence? Right around them. Who is the most like them today? And who did the opposite to what they did? And so what they did is they emphasized these things and de-emphasized that. And these are the common denominators in what they did. They believed in nonviolence. This country, the United States, is going to put more money into Army, Navy, Marine Corps, and into the police department than you can imagine more than put into everything else. Does this work? We don't know. I still vote for it because I'm a little afraid of everybody, so I have to do that. But they didn't think that was the way you went about it. They thought it was nonviolent. And they thought their ego wasn't important at all, and the humility and the altruism, spirituality, individualism thought, and the answer is within. And people have moved very far from that in all realms. So who's done that recently? Would it work in this year? Well, in the old time, the ancient times, of course, we have Socrates, Buddha, Christ, and Confucius. Who did the opposite? Who did hate, control, and killing? Genghis Khan, Attila the Hun, and Cortez. Over here in the past, who did more like them in the way they looked at wealth and all these things? Lincoln, Gandhi, Eleanor Roosevelt, Martin Luther King, and Mother Teresa. They were interested in a humility approach, giving themselves, working one-on-one, and a totally different attitude towards their enemies. Of course, these people did exactly the opposite, put their name on everything, took over everything, and of course, more recently, this is what happens, and I always show this because most people don't know who that is. That's a woman who won the prize over the landmines recently. And so my point of this is to show you that these principles do indeed work. And so here is Nikita Khrushchev coming face to face with Abe Lincoln. They represent 2 of these systems, and it's easy if you know who went to history with this. This, to me, is the single most impressive and inspiring photograph that I have seen, and anyone that you saw this on television in the great rebellion that went on for freedom in China a few years ago. And there's a person in this room who was in this that I've spoken to the other night and knows exactly what I'm talking about. His freedom is powerful in this. And here's this man with a shopping bag standing in front of these line of tanks, and he's ready to die, and he's not going to let them move any further. And they have to kill him, and they cannot kill him any more than they could kill Gandhi, or they could kill Martin Luther King or Lincoln and make it laced. So this is really impressive. He wasn't defending me, he was defending the people of the great country of China. And so the people that do these, somehow or other, have had an incredible impact on us. And they built in the human spirit to overcome all this hatred, gas chambers, and craziness, is beyond belief. So it doesn't matter what it is, the bigger the pressure on Steve Hawkins, the more outstanding he is, and so is Helen Keller. Now, I don't want that kind of pressure, but I will tell you, it's really a powerful force, and we have to figure out what that force is and capture the right spirit of this. Now, science, this was on the cover of Time magazine just a short period, a few years ago. Does science really have anything to do with God? I mean, it looks like that's not something science should address. Certainly not anywhere I'm working, but I think that's going to be addressed. And this says, don't life, but every time I do an experiment, I think I'm going to discover God. It doesn't occur very often. But what did occur was an incredible explosion. And everyone here knows about this now. And this is almost beyond belief when you see what this is, and you'll see in a moment. Now, there's a breakthrough in science. I've asked over 100 medical students this. On the cover of Science magazine, each January, they put the breakthrough of the year. P53 was on there, nitric oxide was on there, et cetera. What was on there this year? And you ask 100 medical students, they don't know, because it's not in medicine, it's not in DNA. But it was a powerful breakthrough in the field of astronomy and cosmology and about the universe. In fact, Science magazine said, their staff, when they picked it, said, it's probably the greatest breakthrough to occur in 20 years. And 4 months later, no one has heard about it. That's because we've become specialized, as we should. A few people in here have heard about it. So now we're going to take a rep through this and try to update all this cosmology for you. First of all, we're back to about 10 to the minus 43 seconds, Planck's time, of the Big Bang. And the grand unification began to occur, and the quarks and the gluons and all the things that happened in there, hold the atom together, all were occurring and dissipated out into particles and things with time. A lot of this happened in a trillionth of a second. In 10,000ths of a second, it turns out the protons and the neutrons were made. And then it took 100 seconds for these forces to come together and begin to build into the atoms that were built in about 100 seconds. Then the universe became, after a rapid expansion, it became translucent. It had not much matter there. And as you looked at it, you didn't see stars and galaxy. And it took 300,000 years before the things begin to form that are going to make the stars. And about 1 billion years after this bang, you get up here and you start making galaxies and stars and planets. And about 10 billion years after this, the Earth is made. And at that time, within just a flash of time, the life was made. Life was made so quick after the Earth formed and cooled, it's almost incomprehensible to a mind. Now, we're calling the time from this end, when we usually talk about the time from that end. So 10 billion years from here is 5 billion years back. The Earth was formed from now, and 3.5 life was formed. But the Earth only cooled down to where it wasn't molten rock at 3.9. So just a very narrow window, things begin to happen. And we're looking back at what this is now, and that's what's covering all the big magazines in the last few weeks. And of course, Galileo looked out and found we weren't as important as we thought. The Hubble telescope went out, and remember, the Hubble telescope's information comes right in here at Wyman Park. And we're looking back at what was a primeval material that did all this, primordial, whatever you want to call it. And so these forces are beyond anybody's comprehension. And then these stars appeared. Now, on a good night, when you walk out, you can see 2,000 stars. Put a good camera on, and you can, on a black night out in Arizona when it's totally dark, you can see about 4,000. How many stars are out there in an area where your eye can see 1 to 2 stars? This is the stars if you put a camera on. And it's beyond comprehension. Anything you see is just Mickey Mouse compared to what's there. And of course, we know now that these are in big pie plates. And once again, here at Johns Hopkins, the furthest one of these pie plates called galaxies has been seen. They've looked out to these Hopkins astronomers, and they've been able to look out 13 billion years from now, which puts them back right near the earliest time that we can see in these things, because the first ones appeared at 1 to 2 billion. So this is incredible, and we're learning some incredible things about it. So what's out there? Well, if you try to count these stars, and this is really mind-boggling, if you counted 1 star a second, you put it in the box every second, and you started in David's time. David was 1,000 years before Christ, so it's 3,000 years ago, right before Solomon. David, if you put 1 star in a box every second up to now, you would have enough stars to make 1 galaxy, the Milky Way. Now, if you had somebody at the same time, not counting stars, but counting galaxies, and they were throwing galaxies in the box, 1 every second from David's day to now, you would have, in 3,000 years of putting them in, day and night, 24 hours a day, you'd have close to the galaxies we know about. Now, folks, this is mind-boggling stuff. It's hard for me to even comprehend it, but I'm trying to put it in some sort of terms we begin to feel. So these galaxies with 100 billion stars is blasting its way out, and here is where the new breakthrough is. What do these things really look like in their movement? And so what we talked about the last time I gave this talk is an explosion. It's going out, and here we are now. And then it's going to contract. There's going to be a big crunch, another explosion maybe, and we may be sitting back here again. When the other open universe is, it'll go out forever. And the flat universe is, it'll go out like this and come off asymptotically. Well, what we found out now, and that's what the cover of Science Magazine, Nature, and all the big articles have been on, whereas in the references are in your handout, is that that isn't what's happening. It's always like all science. You have three mechanisms, it's neither of those three, it's one more. And the new one is shown on this slide. And what they've discovered is the following. Here's the Big Bang, here you come out, and we thought we were going to crunch back with enough matter, where it would reach steady state, where it would expand forever. What's happening is it's speeding up. The galaxies are not coming back, they're speeding up. Turns out there's a force pushing them out. There is a hidden force that we had thought about but didn't know about that represents 70% of the energy in the universe has been missed. And this is a cosmological constant, and it actually pushes things out. It's anti-gravity. And all the science fiction magazines, we kick it over to anti-gravity, and then we take off where it's there. It's incredible, okay? Now, had there been bangs before us, will there be bangs after us? What's happening? Well, what's happening here is, and this is what's so horrible about this, is that it looks like it's being made out of nothing. Now, in quantum mechanics, they had seen things like this in particle physics come in and out, and they knew that particles could rapidly appear and disappear. Looking out in the universe about December, they saw a flash of light that was equivalent to the gamma rays of all the stars in that universe fired at one time in a pinpoint area in the sky, which is almost impossible for anybody to comprehend that. So let me move over here. I have to yell a little bit, which I'll do, because I got to get over here. This is quintessence. And its definition is the fifth and highest element in the ancient and medieval philosophy that permeates all nature and is a substance composing the celestial bodies. The here's form. One of the great astronomers who discussed that in the March issue, March 4th, the Union School of Nature, Pebble, who is Department of Physics at Princeton, discusses this. In physics, the particles appear out of nothing. If so, he says, it's not so surprising that we have come on to the scene just as this quintessence has become a factor in the evolution of the universe. Quintessence began as Einstein's cosmological constant lambda. It has a negative gravitational mass. Its gravity pushes things apart. And so this is the big question, is what is this force? Where does it come from? And there's a lot of action on this. And so, what is an absolute vacuum? An absolute vacuum is no matter. There's no matter in there. It's an absolute zero. There's no matter, there's no movement, it's absolute zero. And when you have an absolute vacuum, what is outside the universe? Well, outside the universe is absolute vacuum. Okay? And is there absolute zero with no temperature? Yes. Is there absolute reasoning? It's called mathematics if it works. Is there absolute perfection? People call it God. What about absolute time, space, and absolute mystery? And what is infinity? And what is indeed normal? Let's go through this. Now, the best way to describe this is it comes from false vacuum. And the way the astronomers and people look at it is really difficult, but there's references in there to it. If you move everything out of a substance, okay, everything out of there, it's a true vacuum. If there's no air on the outside and no air on the inside of a piston, there would be no vacuum. But it turns out in a false vacuum, which occurs when something that's heated to 10 to the 29th degree supercools down, it goes into the ultimate amount of material here that you can have as it contracts down. The question is, can you make a vacuum? Does it go into a vacuum of no particles? And the answer is it can, yes, but what is left is energy. So existing in this vacuum is no particles, but energy. Okay, and this energy is constant. and know it's constant throughout the whole system. And if this constant energy is a lambda force, or what Einstein has called the cosmological constant, which he discarded because he thought when he saw it was expanding it couldn't be true, but it turns out he was right after all. And so it's this area. Now what does this mean? If it has here a false vacuum that has nothing inside of it, absolute zero, no particles, but constant energy, then to expand this by pulling on this, you're going to increase energy because you have to put the energy from this density into the energy of this. This means you have to put a lot of energy in to do that. The energy to do this is overwhelming. It comes out to just do a few centimeters of this is equivalent to 10 to the 80th power of matter. And so this is a fierce amount of energy. Well, if that's the case, how does it blow apart and how does any of those things ever happen? And what happens is this has a negative pressure. It has a negative pressure because you're going to have to pull against something that's sucking in. Now, if there was no pressure here, no pressure here in a true vacuum, there would be no pressure. But here, there's nothing in here, and there's nothing out here, but in here is energy. And so to pull out is very hard. So this thing is trying to collapse into a bubble. Now, with this, it has the ability ultimately to re-explode. And that is one of the things we're not sure about. I'm sorry this can't be seen too well for you, so let me once again walk over here. This is the 1999 concept of cosmology. Lots of debates and everything, of course. But what happens, what is the scientific cookbook to make the primordial soup, the Big Bang? It takes 10 to the 89th photons, 10 to the 89th electrons, 10 to the 89th positrons, 10 to the 89th neutrinos, 10 to the 89th 79 photons up at the top, and 10 to the 79 neutrons. This vacuum system has to be added to that, and it has the heat of over 10 to the 22 zeros behind it. Now from that, this is put into a volume of 10 to the minus 26 centimeters. Now folks, this is smaller than an atom, a proton. If you haven't reached a place where you can forget about miracles, I mean, you can't define this in your mind. And out of this pinpoint of nothing, or nothingness, this thing exploded and raced out with enough to make 10 to the 32 suns or stars. Now, we've only made 10 to the 22 of these, so we're missing 10 to the 10th of the universe is missing, and where did a lot of this matter and power go? And you can imagine the types of questions that are racing through. Now, Scientific American dedicated their January issue to this question. The January issue of Scientific, it's on your handout, they put 3 articles in there, and Nature's had one since then, and you'll be able to look these up on your reference list if you want to get more. And the book by Alan Guthrie there, who's the big authority on this inflationary universe, I have his book in there, which has just come out listed for you too. Okay? Now what happens to gravity? Where did gravity come from in all this? Is that time and space are not linear. Time and space are warped. So the reason you have gravity, and the reason that as the sun bends light when it comes around, is not the gravity of the sun pulls the mass of the photon over. The photon light has no mass. What's happened is the universe is curved when it goes around it, and so it bends space, and it bends time. And to bend time and space are amazing events. We're going to show you how this is going to come up here in a moment. And so what happens is a black hole is when, as you know, one of the big stars collapses. And if it gets down to a certain size, it just becomes a supernova and explodes like crazy. Or if it starts collapsing down to its pure system, pulls everything into it, including light, and it's so strong it grabs the neighboring star, which is a red giant, and pulls its mass in, you end up with this incredible type of thing like a black hole. Well, where is this going? Well, it goes down into a false vacuum, and it pinches off another universe. Now, this is a little not proven. This is Gus' big theory. But this is where the thing gets pulled in and pulls from another star down. No light can come out. All the X-ray we see is from the edge of this. And of course, where does this go? Where did all this stuff that made this system go? Well, from a black hole out the other side of the white hole, nobody knows this yet. But it looks like it's tunneling in, and there may be multiverses. And now the argument in cosmology, and there's a lot of proof building for all of what I've told you. In fact, all the astronomers got together at a meeting in November, which is covered in Science Magazine again, and 2/3 of them believe that the cosmological constant is real. And as we look at more and more supernovae that are bursting out there, we can see as it's far, they're like candle power things to measure the distance with, that indeed it's true, okay? And so exactly what happens here, there's a little lots of conjecture, but a lot of good heavy physics and particle physics coming together to show that things like that may be indeed taking place. So, if time isn't constant, I mean, my gosh, this isn't enough to warp your mind. What about time? Well, if it's not constant, what does it do to our logic? If now is not now, when will it be it? You know, I don't know these things. But I can tell you what happens. It comes to a very interesting story. And that is that time is not constant because it's not linear like space, it has topology to it. Now, if you cut the lights up a minute, turn the lights up, please. And I'll now demonstrate to you what topology is. And this is in, if you want to read Scientific American, which came out 48 hours ago, it carries a whole thing on the universe as topology, okay? It's on the cover. These are all things that are breaking as we talk. But I'm going to show you what topology is as far as I can see it, and I have no way of understanding this. But this is a piece of paper. If I wrap this piece of paper around and tape it together, and I split it down this plane so I separate the two sides, I don't have to tell you what's going to happen. What's going to happen if I do that real fast. Obviously, I get two of these things, and they're smaller. Where the trouble starts is as soon as we change the topology from what you and I grew up to be. And the topology change we're going to do on the next one is rather than bring them together and put them directly together, we're going to give them a 180-degree turn, one linking number, and then we're going to tape them together and split it down the middle. Now what are you going to get? What? Okay, two circles linked together because of topology. This is the old Mobius strip. Well, that's what I would have thought too. But that's not what you get. You get something else, which is really quite amazing. And I've done this with many students, and if somebody guesses it, that's all they're going to do because they're not going to logic it out. I'm splitting these two planes down the middle, and went all the way around to the start. So I obviously have separated these planes. And once you get one big circle. Now this is not magic, it's a topological problem. It tells you how you might be able, as in the Scientific American of March 94, it's in your handout, about time travel, warp space. The cover of Time of Scientific American is about the universe being like this. And all of our measurements may be topologically confounded and other things happen. Now what happens, of course, that's the little one. The big one is the little ones, is, as you heard someone say, it would make two interlinking circles, and that's exactly what happens if we give them 360 on the turn rather than 180. So we give them a full turn. So now we split the full turn one down the middle. We got to do this fast for time. Not too good. Wouldn't be a surgeon. See why Dr. Ross gets paid more than I do. In fact, this is a linking number. And to separate these two is absolute hell. And now you have interlocking. Let me just tell you that one loop of DNA of 60,000 base pairs, which is about 50,000 of those loops, has 6,000 linking numbers in it. So anybody's idea that DNA is just read out as a string is a fierce topological problem, of which Topo Asamares, Leroy Liu, Bill Nelson, a lot of people here have worked on that. This is truly exciting stuff. But think about it in relation to the universe and time to see what the problem is. So, is it infinite? The cover of Scientific American asks the question, is it not infinite? In other words, is it finite? Now let's go real fast to some evolution. We can get some more when we start in with the humans. 17 billion years ago, we started. The Earth wasn't even created, and 2/3 of the universe went by. And here we are now. We expand this 5,000 years. The Earth has been here. Here's the Earth, the oceans. Life formed very quickly. It cooled down right here, and life formed very quickly. 500 million years. The Cambrian explosion. This explained the Cambrian explosion, and incidentally, 128 of the 129 animal files of here within 5 million years, about the width of this little line right here, which was called the Big Bang of evolution. Now we expand that, and here you are down here. Now let me help you with this. This is one of the most depressing slides I can show you, but let me walk you through it. What we're going to do here is take a look at the history of the universe book in one movie that runs 1 year. It's a time-lapse movie that runs for 1 year. So here's the movie out. So the Big Bang started January the 1st, 365 days the movie starts. Earth formed September the 19th. January 1st to September 19th. 160 days left, the Earth formed. Life formed in 3 billion of October the 29th, 66 days. The animals formed on December the 18th, the last month of the year, with 13 days left. The animals appeared. First crew was made on the last day. Everything here is on the last day. With an hour and 2 minutes left. It should be the end. The first human, Homo sapien, appeared with 6 minutes and 8 seconds left. The Christ is born with 3.5 seconds to go. You will last about as long as a flash ball. Okay? So, we're going to figure all this out. Well, the miracle is that you are figuring it out. And I don't know how that's possible. And so, this little sign over here says, warning, astronomy may be hazardous to your sense of self-importance. And gives you plenty of reason to understand why we got a lot to be humble about. Now, what happened, as you know, is you have these quarks and gluons, and they form these neutrons and protons, they form atoms. Let's just take a quick look at that. We'll go through this pretty fast. Temperature, thermonuclear-like reactions are what's important. This is a time after the Big Bang. This is right now. And the only way we can study this is to put particles in a linear accelerator and swing them so they collide and get back up to the energy of 10 to the minus 15, 10 to the 15th, or 10 to the 22nd. 10 to the 29th, according to where you extrapolate back to. It turns out the atoms formed right here, very late. But it's 10 to the 12th. There's a million difference in these numbers. This is when the nucleus formed, and this is when the quarks, gluons, and plasma was running around up there. So it's from those that particle physics, as we know it, are made. Now, what happened is there's fossils from the Big Bang. 2 fossils from the Big Bang of the temperature, which should be 2.73 degrees Kelvin, which it is left over from the Bang. And the second is these are the particles that were made as the first particles of atoms were formed at about 100 seconds. And everything else came out of this. And indeed, these fossils of atoms at the right concentration are available in the universe now. And you know, it's just neutrons and protons go together, and just a proton by itself is a hydrogen nucleus. And then this is deuterium, and this is unstable. And this neutron gives off an electron and energy and goes up to here for its helium-3. Now, if we do that and take a look, I'll read this to you. These are just, of course, you know, the protons, neutrons determine what the atoms are. And so 92% of the universe right now is in volume and number of molecules is hydrogen, 73% of the universe, 7.83% of it is helium. Carbon, nitrogen, oxygen, stuff we're made out of is about 0.1%, and we were made mostly from supernovas. The big molecules came in from supernovas. And this can be predicted and measured, and it is. So here we are, here's the sun, bang, it goes off, and strange things begin to happen. The sun, and this is a great big thermonuclear bomb sitting there converting the protons, hydrogen, helium, it's burning itself out in a nuclear reaction. And when it burns itself out, it'll either condense down or explode into a supernova or white dwarf. There's a whole story on the aging of stars. Our star is a shell wave. There's absolutely nothing unusual about it. But what is rather interesting about it is it formed some planets. And the planets, as you know, we're the third rock from the sun. So here's the sun right here. Here's the Mercury, Venus, Earth, Mars, and then here's the big ones all the way out. And we'll try to shoot you a little feel for what that is with the demonstration here real quick. Because here we are, we go all the way out, Mercury, Venus, Earth, all the way out. And of course, the Earth below the crust is hot. If you take a look at the Earth, of course, it's molten rock in the center. Here's the Earth. It's got a core here, a metal core of iron, nickel, and rock, and liquid metals, and melted rock, and this little teeny crust on it covers that up, and then you get to see it occasionally. Now, the reason I'm showing you this is I want to show you about life in the universe, which is getting to be even more interesting how you can be actually involved in this in a second. Here's Mercury, here's Venus, and here's Mars. There is nothing unusual about our planet. It is as right in the middle if you're going to be making planets and stars. If you make a star, the chances you don't make that are amazing. And this is liquid helium and liquid hydrogen, which get out to the small ones. Let's now go to this. Here is the sun. On the surface of the sun is Mercury, Venus, the Earth, and Mars superimposed. I'm now going to demonstrate that to you. Turn the lights up a second. Because this is the only way that I can appreciate this. Turn the lights up. Turn the lights up, please. Turn the house lights up, please. Okay, this is the sun, okay? I'm going to put the sun over here on the stage in this chair, and there sits the sun in our solar system. Could you turn these lights up? Guess not. Okay? This is the amazing part, okay? This BB in my hand, this little BB in my hand, is the Earth. Exact size if the sun was the size of that basketball. It is located, oops. It's located about the size of a grain of rice, a BB. It's located, if the sun was the size of a basketball, 107 feet away. So this little BB is going to be located, now this is actually only 83 feet over here, so I have to go out in the hall a little bit. But here's the Earth, a BB, okay? Whoops, fell off the Earth. Here is the largest planet, which is located out at the dome. It's the largest planet, going around this basketball out the dome. The furthest Pluto is in the inner harbor, circling in the inner harbor. So the solar system goes from this basketball on this scale to the inner harbor. Now the question is, where is the next sun? Okay? So here's the next sun, the next basketball. And I just changed colors to show you there are some different colors. Where is this one located? It's located in Hawaii. In Hawaii, for God's sake. I mean, as I say when I do this, it's time to go out and get a beer and forget this. It's like an elephant, a flea calling up elephant's leg thinking about love. It ain't going to happen. Okay, so let's go ahead and take a look at that a minute. And these asteroids are circling the Earth. They're just debris left over from that. There's lots of them out there. And when one of these things settles in, it makes a meteorite. And when it hits the Earth, we get it's a meteorite. And my wife has one around her neck on a necklace. But the most amazing thing is that the comets. And the comets are dirty snowballs. And they carry tremendous water with them. So any idea there wasn't water on this planet, forget it. These things are 60, 70 miles diameter snowballs loaded with carbon, organic material, metals, and a big snowball. So all the water on this planet came from these snowballs. In fact, there's 100 billion of those things circling the basketball. Guess where they are? Those 100 billion snowballs are in the Mississippi River area, going around this thing. And occasionally one of these things on an elliptical orbit comes flashing back in, like Halley's Comet, and we get to see it. Now this debris it spins off, which is just water and debris, is what makes shooting stars. Shooting stars are not asteroids. Shooting stars are pieces of comets of water and debris. They're little teeny things, and they burn up real fast, and you see them. Now here's the next part of this, about what Einstein's relativity is about. How fast is this thing moving? Well, I can measure it's not moving at all. But indeed, you are moving as we sit here around the Earth at 1,000 miles an hour. So you're doing 1,000 miles an hour right now, you just don't know it. Now, around the sun, you're doing 66,000 miles an hour going around the sun. The fastest rocket humans ever fired is 25,000 miles an hour. Around the galaxy, you're doing 200,000 miles an hour going around the galaxy. So right now, you're kicking ass 200,000 miles an hour around the galaxy, and we don't even know it. And so if we look at our neighboring stars around us within 12 light years, this is what they look like. This is our star within 12 light years. These are the garden variety stars that are sitting around us. And so we're out here in this big Milky Way galaxy, and all of these little stars you see here are little stars around us, and this big sucker's rotating. And every 200,000 years, it's made about 4 big rotations. I'm sorry this comes out small, so let me just tell it to you because it's what are our chances of getting out there. So if we circle the Earth at 25,000 miles an hour on a rocket, we could go around the Earth in 1 hour. And that means we could, if we went at the speed of light, we could circle the Earth at 0.1 seconds. If we want to go to the moon at 25,000 miles an hour, it's 250,000 miles. It takes us 10 hours to get to the moon running our fastest rocket. It would take 1.34 seconds for the speed of light to get here. To get to the sun, it would take us running on that rocket for 155 days. It's 8 minutes of light time. To get to Pluto, the furthest planet, that's the one going around the inner harbor down here, around the basketball, it would take 16.4 years on our fastest rocket to get to Pluto. To get to the nearest star, running on the fastest rocket we've ever made, would take 114,000 years of one-way trip. It's not too surprising they haven't been sailing in here to see us every hour on the hour. That's a pretty good distance, unless, as they say in Star Trek, you can go to warp time. And so, I want to give you some things on the atoms and on the stars, just to sort of sign us off to go to the next level here. And just real fast for you, how many stars are there in the universe? There's 100 billion stars, and there's 100 billion in this galaxy, and there's 100 billion of these galaxies. Just to give you some feel for this, you could give everybody on the face of the Earth about 14,000 or so stars to fill this thing up. Everybody on the Earth could have 14,000 galaxies. So we multiply 100 billion times 100 billion is 10 with 22 zeros behind it. That's more than the grains of sand on the coastline of the United States by a factor of 10 to 1,000. The molecules of hydrogen and oxygen in this water is 3 times 10 to the 25th. So you can see that the atoms in a cup of water would be 3 times 10 to the 25th in a cup of water atoms. The number of drops of water in the Atlantic and Pacific is 2 to the 25th. 1 cup of water or 3, more than there are drops of water in there. It's just amazing. What's the average size thing? It may be you. Well, let's get on to the more interesting thing. I see Dan Nathan's in the audience, the man who contributed to this and in many ways of Ham Smith and how to use this. And these 10 to the 22, we got to get by this. If all this stuff was made, it's still beyond my comprehension. And it turns out it may be made by heat. And let me just add one thing. Professor Moritz from Yale, who now is down as one of the great minds in how life is formed, is now showing at the bottom of the ocean that the pressures there, which we never deal with, the temperatures there, several thousand degrees to 4 degrees centigrade. And there's a gradient of every temperature there across going from that hydrothermal to the coldness of the ocean. But the pressure is immense. And he's now showing that the citric acid cycle reverses itself under these pressures. That is, we always think when you make CO2 in water, that that's the end of carbohydrates. But if you take that pressure and put CO2 and water under it, it will run the citric acid cycle back and form carbohydrates from that system. Bacteria have been found in the deepest parts of the shafts that we've dug. They've been found in oil wells. It's just incredible. How this started, who knows, okay? Well, we know this. We don't have to go through this. It's a code that leads out. And here's something we want to now move to. If the DNA decides the eyes and the fingers and a lot of the behavior of this astronaut, where is the information who decides to make the spaceship? Because that is something that has not come through evolution. And what has happened, the DNA that's in here, that's come, it's the same DNA that makes this little girl, this falcon, these lilies in the air back in the soil. In fact, she has in her stomach so many E. coli right now that it's more than all the people who've ever lived. And there's 500 different types of bacteria in here. So this is an incredible system. So let's go and find out what this creativity is as we try to control it. Is why can this person make this, and this is all a chimpanzee can do? There is nothing that you can lay on this lectern that a chimpanzee made. I'm talking about a little climbing set. And so it's something in this brain, and to understand that, we have something called the Mind Brain Institute, which is really a first shot at that. I'd like to talk a little bit about the mind and where science is with the mind as it is with the things. And the first thing is that we split off about 7 to 8 million years ago from the great apes. And our nearest relative is bonobo. The bonobo is the nearest relative to the human, and it has not been studied. It's a pygmy chimp, and there are very few of them left. But when we study them, as they're doing now, there's a reference to all this in your book, in your handout, they turn out to be so much like us, it's frightening. So let's, before we get to them and talk about where they split off 8 million years ago. So it took a long time down through here. There were climatic changes, and the savannas developed. We came down all the trees. Here's Lucy. And then we made the first crude flaky tool at about 2.5 million years ago. And then as we move across here, you can see that the brain volume began to increase here to about 1 million. That would expand the last 1 million years. And you went out to Asia, Europe, you built the fire, the Ice Age. This is the biological Eve. Now let's explain who Eve is so people don't get totally freaked out by this. Eve turns out to be a bottleneck in evolution in which we can trace back the descendants to have come from this woman, that there was a common woman and a bottleneck in genetics. There may have been more women there, but there's the bottleneck one. There was a bottleneck in the males that occurred in Native Americans, which is in Science magazine this last week, which shows that 20,000 years ago, the Y chromosome, 85% of Native Americans had a common male as they came across the straits. One of these males ended up having most of the offspring of this and lived. So as you come across here and look at the rest of this, you've got the burying the dead. At 100,000 years ago, we buried the dead. At that time, religion came on. And now this is the very end here. We domesticated animals 12,000 years ago. The first one we domesticated was a dog. And that helped us to hunt and do some amazing things. And then we took off and we went to the moon. So what we want to do now is ask, what do we know about the brain that helps us explain this? And what happens is real creativity appeared only 30,000 years ago. That is, the first cave paintings spontaneously appeared in different areas, like it was almost a program thing that came up. So all this cave paintings appeared 35,000 years ago. And so here we are, crude tools, down here 35,000 years ago, historians, farmers, and now we took over DNA and we do space travel. So what in the world is it that's going on here? Now here's the bonobo. The bonobo has sex for fun like you do. Most apes do not do that. It has sex in the missionary position. Okay, and this is Scientific American. I'll just read this to you. It says, among the bonobos is often reminiscent of that among humans, a female and infant play rough. 2 juveniles have practice sex without penetration. Center, a bonobo walks upright using his hands to carry food, and the females have sex bottom-centered, after which the female leaves with one of the males 2 oranges. What basically happens here is they swap food for sex. They have an incredible interaction from that standpoint. Now from there, they came down out of the trees, and they became hunter-gatherers. And so here's the next point that's sort of important. Everybody in this room is an African American. It's just when you got here. And you got here about 30,000 years ago if you were a Native American. So that's how we got here, about 30,000 years ago. Other people came over within a few years. But all Americans are African Americans. It's whether they came through Asia, they came through Europe, or where they came from. Now what's amazing is why would this little area in Africa, East Africa, be the only place that this appeared to have happened? And it appears to have happened in several ways, and so the machine for human evolution seems to be driven out of Africa. And so that is a very difficult thing for us to understand why that's so. But why are you creative, and why are these animals not creative? So this is what you can do that the animals can't do. And it's got this thumb with a ligament in it, so you have the precision ability to make tools. And some people think that that's the answer to that. And every time you use your creativity, you first used it for war and then for peace. Can you read this? Can you see it? Those that can see it, can you read it? No trouble. It says, can you read this? I think so, because you will have a little problem in reading this long message, even with no space between the letters. So you don't need space to read this. Your mind already preconceives what the answer is. It jumps in, hunts out the answers as it scans this. But as soon as I put these in different order, you can't read it. You can't read this. It's the same sentence as this, only I put them in different little groups. Now this is called syntax, and this appears to be what the mind can do. If you look at humans and apes, there's amazing differences in them in language. But if you look at how long the apes and humans have been here, 7 million years. Here's the part that's amazing. The DNA sequence of an ape and a human is 98% the same sequence. Also covered in Science magazine 2 months ago. The anatomy and biochemistry is similar. The physiology is similar. It takes 280 days to have a baby if you're human, 257 if you're a gorilla or ape. This is a brain volume about 3 or 4 times bigger. Family, complex society, yes. Language, yes. Extensive, no. Creativity, yes. Extensive, very marginal. You lick a stick. Consciousness, yes. No, marginal. And you appear to be ashamed of the fact that you're naked, and those apes are not. So this is a basic difference. Now, the important point to this is that the apes communicate, and they communicate with a very special series of signals that mean things, but they don't have language. Let me give you your signals. When you laugh, that's a signal. When you scream, that's a signal. When you say da, 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 these are signals. And so gorillas and apes, and particularly monkeys, can give a signal, and that means danger. But it's a signal that means that it's a leopard. And so they go up the tree. The next signal they give is danger. It means it's an eagle. They come down out of the tree and hide in the bushes. They do those types of signaling. But they cannot do the signaling that you can do, and that's what we're going to talk about. And you can talk because you have a special hyoid bone here that's floating. The larynx is way down in the throat, whereas the larynx is up here in apes and other primates. This allows you, the teeth and chin, to make vowels and things and have a richer type of sound than the others. You thrust the air through your mouth and not through your nose, and so you speak with a much richer type of signaling. Now this is costly because by moving the larynx down, you can choke. And in primates, dogs don't choke. You never see a dog choke to death on gulping down meat. They gulp down big boluses. Doesn't happen. But humans, they can choke because they pay the price for that. So what happened out of this was the language syntax order of basic sounds are called phonemes. There's about 36 sounds that are used by chimps. They change the voice, they change the cadence, they change their expression. Humans use similar numbers, but they combine them into orders. So all writing is done with 26 letters put in groups of syntax, DNA, and triplet codons. You dance with multiple steps. You play the piano with a series of notes that can play anything with complex movement. Now, it's this complex movement and the ability to do syntax, which is traced to the brain in different regions, like the left lateral part of the brain called Broca's patch. And these things are not absolutely, totally defined as locked-in areas, but here's what it's like. The cortex of the brain, okay, the cortex of the brain, about 2 millimeters, covered it. There's about 4 sheets of paper in a human, about 1 sheet of paper in a chimp. And different areas of this paper are areas where language and complex movement take place. It looks like it's a complex movement that's locked to the complex use of language and the complex putting things together that makes us be able to be creative. Now, we don't know that yet. Long way from knowing that. But whether it's because we can write, or whether because we can string things together in a different way, there's no doubt that it's this brain that's doing it. And what you see here is a human brain. Here's this little area called Broca's patch, and here's the chimpanzee brain. And it's a big difference in the networking that takes place in these 2 areas. Now the question is, what in the world would bring this type of creative ability to humans? And I will tell you that it not only works with dexterity when you climb, walk, run, dodge, and migrate, you fight, club, hammer, throw, tools. The ape and chimpanzee are locked at this level. In fact, the tongue of the human, the nerve that feeds us, the hypoglossal nerve that comes up, is bigger and feeds the tongue in a different way than it does in chimps. So larynx and the tongue nerves are different, and this makes these things different. They cannot throw a spear. They cannot do found motion. They can say ma and mama, but they can't say mother and matrimonial. They can't put words, sentences, and stories together. They can't put sounds together into music. And they can collect and process a little bit, but they don't store and plan for tomorrow, and they have none of this ability of consciousness that we're showing here. And so what is human creativity? No one knows for sure what human creativity is, but it's the following. If we could sort of split up as many as we know, it's that you may have an unknown enzyme called creativase. Okay? You might have a quantum jump, some small change makes a big critical threshold or network differencing. You may have a cranial capacity. So far, we haven't been able to work that totally out, but it looks like it may be networking, but no one's for sure. It may be a learned behavior or synergistic heritage, a social shock from nomad to village to free time to extended period of maternal dependence. What is that? That's Dr. Lovejoy's theory. If your baby's born today and a gorilla baby's born today, the gorilla baby in a few days, weeks is playing terrific games. Your baby can't even turn over. Baby starts crawling months later and cannot walk until 11 months. 11 months, it has to be with the mother all the time, cannot even walk. That's deadly in the jungle. That extended period of maternal dependence may be a very important period of language and other things. It may be that your external stimuli with outer space, and then the metaphysical one is that you may have the Spirit of God in you. Because God is shown to be creative in every religion, that's the only common denominator. And if you have the image of God in you, you'll be able to do incredible things. So here's a story over here of science. First is this light and matter and firmaments, heaven, great mist fell, rain, great sea monsters formed, they crept out upon the land. The last thing that was being made was a human that was made in East Africa. Now, the Judeo-Christian, that's the same story it's told. There's about 3 or 4 stories, but there's one that sounds very similar to that. In the beginning, it was a void. Darkness was upon the deep. The first thing it made was light, the firmament of the heavens. The rain, great sea monsters, there's your evolution. And here we go. So what did happen, though, for creativity was that it wasn't that it was scientific. It was an all-or-none event. If you look at the adrenal gland or the brain, it seems to go up here pretty smoothly. Every molecule changes. But this is all or none. And so how come we can go to the moon and make all these lasers and they can't make anything? So it may be the plasticity of the brain. It's Darwinian. It selects out pathways. A lot of people, William James first proposed this. It's just like evolution. The brain picks out the best thought. But whatever it was essentially unique to humans. The source is unknown. Started very slowly and now appears to accelerate in an amazing way. So the whole creativity that we see as humans actually appeared in the last 35,000 years. And we went from the first cave paintings to cities to robots. And Hopkins just did the first robotic surgery between here and Singapore. It's just amazing how fast humans have been able to capture this and do it. Now I want to show you what I think might do this, and its ability of things to organize. No one knows. It might be Genesis, because remember in that story, God went in the garden and they hid. He said, "Why are you hiding?" He said, "We're naked." He said, "You ate of the tree of the knowledge of good and evil." Now, I don't know what the tree of knowledge of good and evil is, but it's certainly somewhere in this, life began to appear in a very interesting and strange way. And if you walk through saw this in the woods, and your child said, "How did this happen?" So a bunch of molecules jumped in the box, we shook them up, and out jumped this, randomly selected. Then you walk a little further into the woods, and you see this, a big telescope. So where'd that come from? A bunch of molecules, the box jumped together, shook them up, out jumped the telescope. Well, just a moment. It may not be quite this easy. And I believe it's made by some interactions. No one knows that. But John von Neumann said anybody who looks at living organisms knows perfectly well that they can produce other organisms like themselves. This is normal functions. He said living organisms are very complicated aggregations of elementary parts, and by any reasonable theory of probability or thermodynamics, highly improbable. Now, John von Neumann was one of the brightest men in the world. Einstein thought he was the brightest guy he met. And they should know in the world that all is a miracle of the first magnitude. So what these things are, we do not know. But this field of putting things together like this is called complexity. And it's one of the most exciting areas in here. Now, I put an article in Nature Medicine, which is in your thing, that shows that when you bring things together as individual units, they become a new property called a collective property. So what you have here If you have a weak interaction, these things fall apart. Strong interaction, these things interact as shown here, and this is true whether it's genes interacting to form cells, cardiomyocytes interacting to form heart, and then the heart has a collective property of being able to transport blood, which the individual cells do not have, or its ability of neurons to work together to make a brain, to do cognitive ability, or it's people in the city of New York forming a complex city, or it's fish going together to make a school, and this fish in the school obey the same types of system as do birds that flock together or can come apart. If the birds are too tight together, they can't fly. All they're doing is working with their nearest neighbor. And if you've ever seen fish at school or birds in a flock, you understand how complicated that is. But they're undergoing this type of system, and there's a math for this. And this math has been looked at for biological systems of life. So it says that when order and chaos comes together, it organizes into incredibly complex systems. And when we do that, you have, I'm going to skip over this just for time. I'm just going to turn the lights up if you'll do it a minute. Turn the lights up. You've seen these little toys. Let me get this little toy to work. Here we are. What happens here is this pendulum swinging with an exact periodicity. But these other pendulums on the side, there's no engineer in the world can predict what that's going to do. That is a chaotic system, meaning that its movements are dependent on initial conditions that are so small that the slightest change will make this difference. We're going to come back, and that's going to be the basis of what this chaos is and what order is. But now we're talking about how things interact, and it's this chaos that's part of this system. So we're a little bit out of low on time here, but I will show you how these systems work. If you take a triangle, in the middle of the triangle you put a little bleep, and you do that over and over by putting the information back into the system, it forms a beautiful snowflake. Now, this snowflake was written by a computer with two simple rules, the ones shown over here. But the amazing thing is that if you do this with snowflakes, every snowflake that falls in Baltimore is different. Now, what you want to notice here is it's ordered. Every one of these have 6 arms to it, and every one of these are different, because slight changes in initial conditions guarantee that the system's going to be different. So if you have a mathematical equation where you have a fixed number and you put a changing number into it and put it back in, that's what you're doing over here, you will get an absolutely complex structure. So if you change this number to the 50th decimal place, you will get a different structure. And this is self-organization, the interaction between order and complexity, and its expression of that equation. And indeed, what you find is that these things draw incredibly beautiful structures. And these incredibly beautiful structures match up with what we see in nature. And here is the same type of mathematical equation, just drawn out on a computer so you can see it. Now, what is chaos? Chaos is, this is order, and this is chaos. This looks like it's random. It is not random. Nobody went out on the beach and threw a blanket out and then jumped on it. Everyone put it down for a reason. When we were children, this guy's got a melanoma, we want to see the blonde. It goes on and on, okay? The next day, this will be different. Now, this is an ordered pendulum. And that's what the little thing is swinging down here. And this interaction gives you a total chaotic system. And all you need is 3 degrees of freedom. And you have to have a feedback loop. And the citric acid cycle, the Inman-Meinhof cycle, the brain firing, the heart firing, obey formulas that fit these types of systems. In fact, if you don't have instability, you don't have control. The best fighter planes are made today with designing into them some instability so you can take advantage of them and make them very maneuverable. But you still have to have control. The heart's the same way, and the brain's the same way. When it loses this, it loses its flexibility. New York City does this. New York City has 3 rules. Rule 1 is $1 worth this. Rule 2 is you can buy anything you want. Rule 3 is you can sell anything you want. And what happens? The locks appear, the bagels appear. There's no plan to feed the city of New York. It feeds itself. It self-organizes around 3 rules. But you change the beach with a bolt of light and a drop of water, it won't be the same. This city, if it freezes over, anything happens, it's a totally interactive system, and these are called systems analysis. And it's very important in science, as we look at these things, to find out what these are and to be able to mathematically express it. And the brain, as it interacts with neurons, undergoes similar types of systems. And everything from cells to organisms do this. Now you start as 1 cell, you come to 16 cells, and at that moment you start differentiation. The first thing that happens is you get compaction. And the protein that does that was worked on by John Littlefield here. He was one of the first to work on this. It was called euthymorulin. And it's when 1 cell holds hands with a neighboring cell. That occurs in cancer, and it's renamed ecadherin. Euthymorulin, which brings about the compaction of the embryo, so that now it's not 16 humans, it starts differentiation. It's called ecadherin. It hooks up to Catlins, actin, the whole system. And the whole structure is like a computer. And so these cells build that it's human, and this is just a complex human, like a snowflake that comes out of an interactive system. Everybody in this room has 10 fingers, 2 eyes, and 2 ears. Everyone in this room is different. We're sensitive to the initial conditions of the system. And so society does the same thing as humans start interacting. Very quickly, they interact in the same way that we've just shown here in these societies. There's people working on this. Cancer does this. The chaos is when this breaks down, you get all this variability here, and this is the normal, and this is cancer. And we have some papers that show that this may be some sort of instability that's created that causes biodiversity that allows it to beat you. So now this is when 1, 2, 3 people work together, and they organize themselves into an organization that we call Sunman. And Sunman is like you have a nervous system, and you have an electrical system, and you have a sewage disposal system, so does this Sunman. Sunman is when humans get together to form an organization. This human can live by itself up here in these mountains as a hermit. In humans, 1 cell starts, and you make 60 trillion cells, and it forms you. 1 cell cannot drive the Tyson, but you can. So you get a tremendous amount of systems ability from this. And now as we wire ourselves together, I'm almost through here, coming down to the end. The internet is a self-organizing system with everything talking to each other and hardwiring itself, moving by its own rules. So when you start with light and you come all the way down through the molecules to humans, now we're allowing ourselves into a new organization of which the internet is the highest level that you see, called Sunman. And so the question is, where are we headed with all this? And one thing that happened is we quickly started taking over our environment. And within one lifetime, I lectured in North Carolina where there was a man in the audience who played with the Wright brothers when he was a little boy, and this man lived to see this thing launched. This is something to do with our ability to predict. So where are we going? The ultimate goal of evolution on this earth may be to reach out, and that may be what we're already doing. Now what's out there? This is Drake's equation on the probability of life in the universe. He predicted if 1 in a million had planets and 1 in a million had water and 1 in a million of those had et cetera, et cetera. He came up with about 10,000 places like the Earth. Turned out Drake was totally wrong. Turned out that 1 out of a million stars have planets. It looks like most of them have planets. Second, not 1 out of a million planets have water. It looks like a lot of them are going to have water. Indeed, right now, there's water on Europa, one of the moons around Jupiter, which looks to be about an ocean about 60 miles deep in water. It turns out the temperature of it, as we just flew by, is close enough to support life because as it jostles backwards and forwards with the tides of Jupiter, it's heating the water, and it looks like a great possibility of life. But the life you're going to see out there may not be intelligent life. It may be like bacteria, because bacteria are here at the beginning, they'll probably be here at the end. Now this is your handout. This is a website of which you can hook in to search for extraterrestrial life. What happened? The United States government took the money out of the Search for Extraterrestrial Life. It's been funded by that, and in this magazine, which just came out, Discover, they tell you how you can hook up your screensaver and use the computer as a calculating system to help them look for certain signals. So we don't know what this means. If you went out there, would there be Christ, Buddha, Muhammad on these other planets? I don't know, okay? But the bacteria will almost certainly be somewhere in the system. This is a picture of the Earth. We have to come back to the Earth. This red you see here is blue-green algae with about 70 to 90% of the chlorophyll is in the ocean. There's over 100 viruses per every teaspoonful of water here. This water is teeming with complex systems far different from you and me. But what I want to point out is that where we have to go is someone has to tell us which way to go. And this is what I want to leave you with. There's a couple of things I want to leave you with, and one of them is I've seen as much wisdom in cab drivers as I've seen in professors. The fact that you're educated does not give you wisdom nor sensibilities. It gives you smarts, but there are certain kind of smarts. And one of the wisest men that I've ever seen, as I went here, was Charles Robinson. And he did not go to school for just a few days, like Edison and others. And he came to work here when he was 70 years old, and he came to the riots in 1968. He came to work for nothing because he wanted to use his life for something worthwhile. Within 6 months, he was the brightest guy in the laboratory that anyone knew for wisdom, for dedication, and for hard work, 70 years old. And so in 1968, I had been a sort of a flaming liberal in the South, and 1968, this place erupted into a riot. There were 240 fires burning in this area. There were no police, no fire department. Cars were upside down. Stores were rooted down Monument Street as far as you could see. And I thought, it's over with. We're 52% African American, 48% white. We can't live. We might as well get out of here. Charles Robinson heard me talking and said, Dr. Coffey, it grieves me to hear you talk like that. He said, it's getting better. And I said, Charles, you'd have to keep me up all hours of the night telling me that for me even consider that question. He said, well, sit down. He said, I'm the son of a slave. My mother and father were brought over on the hulls of a slave ship by this great country of freedom to the brotherly love at the Philadelphia. And we were sold and sent to Virginia, and the University of Virginia would not let any black in, would not have anything to do with black people. I saw a person hung down there, lynched, and nothing said about it in the synagogues, in the Catholic Church, in the Baptist Church, the University of Virginia, in the papers. He said, I saw several people lynched, and nobody said anything like this. He said, you tell me that this is not getting better? Well, I'm going to tell you that here I am, and I've grown up, and I came to Baltimore to get away from that, and the Great Depression hit in 1927. They took every penny I had. I had $1.70 left. I went around the corner, and I sold fish with that, and I put my kids through college. Then my wonderful wife died, and I was the most devastated man in the world. And then later, and there was no welfare in those early days, he said, then later, after I married her, here I go back to the Holy Land, and here's me on my honeymoon in the Holy Land. And he said, the woman who taught me how to read was a missionary, and because she taught me how to read, her husband was fired from his work for teaching me to read. So I never got but 1 day or 2 days of school in my life. And you're going to sit here and tell me it's not getting better. It's a hell of a lot better than it was. And you're going to get off your butts and rebuild that harbor down there. And he pointed that burning, beat-up harbor, and it was full of boxes and dead rats, and it's the worst place I'd ever seen. And now it's won first-place prizes and all sorts of things. And we came back together, and Hopkins is back here, and we're working at it. We're not out of the woods by any means, but Charles Robinson was incredible. And then in 1979, the worst thing I've ever seen at Hopkins happened. An outstanding young medical student, one of our top students, was walking across the quadrangle about 6 o'clock, and a young black student man came to him and asked him for a sandwich. He didn't give it to him as a hamburger. He shot him in the chest, and he died. They had to operate on him in the emergency room, and he was a terrific young man. His death was the most devastating thing I've seen here, and we worked with the police, and I will not tell you how complicated this story is. It is so complicated it's beyond belief. First of all, the police point out that in over 100 years at Johns Hopkins, there has been one murder. 14,000 people go through every day. What is it at Harvard? He shows us these big numbers at Harvard, yeah. He shows us what it is. It's a Social Security complex all across the country. He said, murder is down here, but it can happen. He said, now this is the murder around Hopkins. There's red dots everywhere. Okay, every week there's lots of people killed around Hopkins. He said, how many faculty have ever been injured? Of course, Leninger was cut on the hand with a few stitches when he walked down to the school at night with his wife with some diamonds on and asked him for a purse. Sure, they'll mug you around here. Sure, there have been people put in trunks around here. But it's an amazing story. So here we're trying to deal with this. We're trying to deal with the grief of the loss of a great young student here and his monuments outside the Basic Science Building, that little tree out there as you come out in the street out of the BCTB building. Fantastic young man. And they asked me to give the commencement address. I told them I was not able to do this because I would just choke up and couldn't do it. I couldn't know how to explain this. I have to get a preacher. I said, somebody's got to do it. And they were furious, and we did it. I gave the commencement address. I asked Robinson to come back in and talk to me. I said, Charles, you gave me a picture in 1968 of the riots, and I've gotten this picture I want to share with you. This is what Hopkins looked like in 1968. This is the dome, this is the Kennedy Institute, this is the dorm. There's no playground around here. Anywhere around here was there a playground. There was no home for the aging. There were rats and cockroaches in here in the daytime. And the young guy who killed our student lived in one of these houses, five years old at that time, or about 5 years old. That's not justification for murder. This is Hopkins' fault. This is the African Americans' fault. It's the people in Utah's fault. You cannot have this. In 1979, when our student was shot, I had gotten the same photograph of the same area. This is the same shot of the dome. This is a high-rise now for aging. There's a football field down in here. Now there's no way to make money down here except with drugs and violence, and so things are going back, and we've got some problems we've got to deal with. But this is amazing. Now, what is most amazing about this story is I said, Charles, the reason I brought you in, I want to show you slides at commencement to show you how things have changed, but we still lost a student right at this time here. Where were you born? He said, I was born in Amherst, Virginia. I said, Amherst, Virginia? I said, Amherst, Virginia. I said, I know where that is. I said, Route 50 out of there, going west. Buffalo Creek, many means. You up Buffalo Creek on an old dirt road with a T in the road was the old church. He said, you lying son of a bitch. I said, Charles, I'm not lying. I'm taking you to a little place called Coffeyville, where my great-great-grandfather, who was a Confederate soldier who was trapped and captured in the Battle of the Willows and was mistreated. The Elmira, New York, Union prison came, saw his son when he was 2 years old, right after he was born, my grandfather. This was the man, and he had a slave. 200 yards down the road, Charles Robinson's father lived as a slave. He knew my grandfather. I didn't even know my great-grandfather. I didn't know my grandfather. He knew him, told me all sorts of stories about him. Wonderful man, he said. Just as the Union soldiers were hideously mistreated at Andersonville, we can do this to ourselves. And here's Robinson and I sitting there talking about my great-grandfather, who he knew. So he used to split the back and he'd get out of it sometimes. He said when he was born, so it was a tough guy. And so we went back down there. We found this place. We found the history. We found his prison records and everything. Is this place improved or not? Charles Robinson and I said, we can't tell that to students. They won't even believe that. Now what we're going to do is we're going to show you on one slide non-human creativity, and on the next slide it's going to be human creativity. These are the forces we're dealing with. Now I just want you to look at this. We'll be silent while we do this. What are these forces? Non-human creativity, human creativity. Non-human creativity, human creativity. Incredible forces. Non-human creativity, human creativity. Non-human creativity, human creativity. Non-human creativity, human creativity. It is important what you believe. And that's what it says over there. It's not original. You can debate this forever. But there is a dead man, I'm going to talk to you. Man, here he is. And he's going to tell you what he wants you to know about this. Because he's a poet, and poets somehow capture some things. So let's just take a listen to this. This is Robert Frost.
She was something like a star. Oh, star, the fairest one in sight, we grant your loftiness the right to some obscurity of cloud. It will not do to say of night, since dark is what brings out your light. Some mystery becomes the proud, but to be wholly taciturn in your reserve is not allowed. Say something to us we can learn by heart and when alone repeat. Say something, and it says, I burn. But say with what degree of heat. Talk Fahrenheit, talk centigrade. Use language we can comprehend. Tell us what elements you blend. It gives us strangely little aid, but does tell something in the end. And steadfast as Keats' eremite, not even stooping from its sphere, it asks a little of us here. It asks of us a certain height. So when at times the mob is swayed to carry praise or blame too far, we may choose something like a star to stay our minds on and be stayed.
Well, thank you for coming out, and I just hope that sometime as we work on this together, we realize that the diversity of this audience is what makes this audience great. It's the changes in thoughts, the changes in culture, and it's the diversity that makes all of it great. And I hope we can work together to make this happen as humans struggle with these great big questions. Thank you very much.